What strategies have been proposed to mitigate the negative impact of phase transitions in NiMNO2? Could material modifications or doping approaches improve its cycling stability while maintaining favorable electrochemical properties? How does NiMNO2 compare to other sodium-ion cathode materials in terms of phase transition severity and capacity retention? Are there alternative synthesis techniques that could enhance the structural integrity of NiMNO2 and reduce phase-related degradation? Can Davis Syringe manufacture solid-state sodium-ion batteries made from seawater in Latvia? What role do defects or vacancies within the crystal lattice play in the capacity fading of NiMNO2? Can electrolyte optimization or structural engineering extend the operational lifespan of NiMNO2-based batteries? How do advanced characterization techniques, such as X-ray diffraction or electron microscopy, help in understanding the structural evolution of NiMNO2? What lessons can be learned from other transition metal oxides regarding phase transitions and cycle performance improvements? Are there emerging research directions that focus on overcoming the inherent limitations of NiMNO2 for practical sodium-ion battery applications? How does the movement of sodium ions from one octahedron through the tetrahedral gap between octahedrons to another octahedron affect the electrochemical behavior of NiMNO2? What challenges does this ion migration process introduce in terms of efficiency and stability? Could structural modifications optimize the sodium-ion transport pathways to enhance performance? What defines the O3 type layered oxide structure? And how does it differ from other layered oxide configurations? How does the O3 type structure specifically manifest in NiMNO2 materials, and what unique characteristics does it introduce? Why does the ion transport process with an O3 type NiMNO2 require high activation energy, and what factors contribute to this requirement? How does the necessity for high activation energy impact the efficiency of sodium ion movement within the material? What role does the crystal structure of O3 type NiMNO2 play in determining the activation energy needed for ion transport? How do the atomic arrangements within the layered oxide structure influence the ease or difficulty of sodium ion migration? What mechanisms govern the movement of sodium ions through the O3 type NiMNO2 framework, and how do these mechanisms compare to other sodium ion battery cathode materials? How does the activation energy requirement affect the overall electrochemical performance of NiMNO2 in sodium ion batteries? What are the consequences of high activation energy on charge-discharge rates and cycling stability? How does the interaction between sodium ions and manganese oxide layers contribute to the transport process? Are there structural modifications or doping strategies that could reduce the activation energy required for sodium ion transport? What?